Okay, so we've got two topics for the day. One is validation, right? So how do we decide which model we want to use? And then the second topic is exponential smoothing. So I'm going to start with the slides, and then we'll maybe put up a whiteboard when we have to do some of the calculations or whatever. We'll see. All right. There we go. No, I wanted. Oh, it's doing the wrong. Hold on. Let me sort out my PowerPoint. It's sharing the wrong window right now because I got a second monitor. Okay. I think I'm sharing the right thing now. I hope. All right. So we want to start with measures of forecast accuracy. So we want to check whether our forecast is doing a good job and how good is it doing. And the way we measure that is just by comparing it to other forecasts. So none of these measures that we're going to talk about today are really going to be anything that, means something in absolute terms, right? There's not going to be any like number where like, oh, if it's bigger than 10, that's bad. And if it's less than 10, that's good. It's not like that, right? It's going to just depend on your data. And we're going to have to just compare to other forecasts, right? If this forecast has less error than that forecast, then it's better. Right? So we always have some error, right? And we talked about this a little bit last time, right? The forecast error is just the difference between the actual value and what we thought it was going to be, the forecast value. Right? So we'll write like E equals A minus F, if we want to shorthand that. Right? Or sometimes if we use a different notation, it'll look like this, right? E is equal to Y minus Y hat. Right? So for the forecasts, there's two different notations we use in this course. Sometimes we use F for forecast. Sometimes we use Y with a hat, right? That also means forecast. So if you see either one of those, we're talking about the forecast. And then for the actual value, we are usually using Y. Sometimes we could use A for actual. Right? It's just notation. So we want to measure the overall forecast error for a model, right? So this one that we just talked about here, right? This was just for a single forecast. For us, if we wanted to predict what are our monthly sales going to be for next month, we could find the error, right? But what we want to do when we're evaluating models is not just look at a single month, right? We want to look at all the forecast errors over a longer period of time so we can get a better idea for what's going to be the best model, right? You can have a model to try to predict something, but if you only look at it over one period of time, you're not going to get a good sense of how accurate it is, because it's just going to be about luck at that point. Okay, so we are going to calculate the forecast error for every value that we have recorded. Right? We're going to see how did this model do at predicting all of these different times. And then we're going to essentially average them, kind of. That's the intuitive idea, right? Just average them. Why wouldn't we just average them? Well, the problem with averaging, just like a straight up average, is that the positive and negative errors cancel out. So if I have one forecast that's off by 10, and then it's off by -10, right? It's high by 10 and then it's low by 10. When you average that out, that averages to 0, right? So it'll look like that forecast is perfect. It'll look like there's 0 error because you're averaging 10 and -10, right? But that's not 0 error, right? That's basically 10 error both times. It's just in opposite directions. So what we're going to do is we're going to try to counteract that. And there's a couple of different ways we're going to do that, and they're pretty simple. So the first one and the easiest one is just say we're just going to drop the negatives, right? If we're off by 10 or if we're off by -10, that's the same to us. We're just going to count both of those as 10s, right? So when we have a 10 and a -10 and we average them, right, we just drop the negative. So we're just averaging 10 and 10 and we get 10, and that's fine, right? So that is the basic idea behind this mean absolute deviation, right? Absolute is an absolute value, as in we make everything positive, right? So this formula says that we're going to take our forecast errors, we're going to take the absolute value, those straight lines there, and we're going to sum them up and then divide by n, which is how many time periods we're looking at, right? So in other words, we're doing an average. We're doing an average or a mean of those absolute errors. Okay, so that's the MAD. That's the idea. Basic, simple thing. You're going to see we're going to do some examples of this, and it's going to be pretty easy. It's also known as mean absolute error instead of mean absolute deviation. So if you see MAE or MAD, they are the same. Okay, so here we have an example where we have the moving averages, right? We have the actual sales and then we have our moving averages that we computed, right? These are our forecasts. Right, these are the actual values, right? So for each error, right? For each error, we can just subtract, right? Actual minus forecast. 16 minus 11.67. And so on. And so that's done here, right? So you get all these errors. And you can see some of them are positive, some of them are negative, right? So we don't want to just average them because that will be wrong, right? If we just average them, then this -10 will cancel out a bunch of positive things. We don't want them to cancel out. Right, so what we're going to do is we're going to take the absolute value of each of them, and that just drops the negatives, right? So the -10 becomes a +10, the -9.33 becomes a +9.33, and so on. So now we have all the errors become positive, and now we just average them, right? We are going to add these up, right? Add them all up, all the way down. Right, and then in the end we get this, and then we're going to divide by how many of them were there. There were 1, 2, 3, 4, 5, 6, 7, 8, 9. So we're going to divide by 9, and that's going to get us our mean absolute deviation. Right, so 6.481. Right, so we take our actual values, we take our forecasts, and the forecast can be using any method, right? In this example, it's using a moving average like we talked about last time. We subtract to get the errors, then we just drop the negatives and take an average. So 6.48, right? That's the mean absolute error. That's how much error we are sort of expecting on a typical month. Right? We're going to be off by about 6.5 on average with this method. Right? Is that good? Is that bad? Well, in a vacuum, that doesn't mean anything, right? Like, we don't know if that's good or bad unless we compare it to other models, right? Maybe this is the best model we've got, or maybe it's terrible and there are much better models. Right? We're going to have to, do the comparisons and find out. All right, so now we have another method, which is called the mean absolute percent error, which is saying that we don't care just about the error, we care about what percentage wrong was it. And so this is recognizing that if I'm off by $10 in this month and I'm off by $10 next month, there are situations where we're going to think, oh, well, that's the same, right? If you think, oh, that's the same, then MAD is maybe what you want. But what if my guess was off by 10 this month when the actual value was 80, and then my guess was off by 10 next month when the actual value was 800? Right? What if I had actual was 80 and then was 800, and so this month I guess 90, and the next month I guess 810. Right? In either case, the error is 10. So according to MAD, those are equal, right? Those are equally good guesses according to MAD. But this MAPE, the mean absolute percent error, recognizes that actually I might want to consider this second one a better guess. Right? Because as a percentage, I'm off by a lot less. Right? I'm off by 10 out of 800 compared to 10 out of 80. Right? So in other words, I'm off by like 1.25% instead of being off by 12.5%. So this MAPE idea says we're going to take our errors, we're going to take the absolute value. So if there were negatives, we would drop them. And then we're going just like MAD, right? So same starting point. We take the absolute value, but then we convert them to percentages by dividing by the actual value to see what percentage error we had. And then we can average those percent errors. Right? These are called the relative errors. Okay, and that's it. That's the idea behind MAPE. So it's like MAD, but with this extra step where we convert things to relative errors. And which one you're going to prefer, which method you're going to prefer, depends on whether you think for your particular situation, are these equally good or is one better than the other? Right? If all you care about in the end is, the absolute amount off you were, then maybe these are equally good. Maybe you want to use MAD. But if the percentage is what's important to you, then MAP is what you want to use. Right? And now there's no like correct answer for this. It's just in your situation, what matters to you? What is going to be considered a good forecast by you and your company? All right, so let me get rid of these annotations here. For this example, right? So we start the same way. We take the absolute value, but then or actually, honestly, it doesn't matter. You can take the absolute value first, then divide, or you can divide and then take the absolute value. In this case, they've divided and then took the absolute value. that's also fine, right? It does not matter which order you do them, right? But the idea is we're doing two steps. We're taking the absolute value and we're dividing. And the thing we're dividing by is not the forecast, it's the actual. We take our error and we divide by the actual value, right? And we get these relative errors. We get these absolute relative errors. And then with these absolute relative errors, we can average them, right? And so how do we average them? Well, we add them up and we divide by 9 because there were 9 of them, right? So in this case, when we add these up, we get this number. And then when we divide by 9, we get the answer, the MAPE. Right, so 3.03 divided by 9, that's going to be something around 33%. Right, so 33.6793%. Right, so using this forecast method, our estimates are off by about a third in the average month. Right, sometimes we're off by a lot more. Like in November, we were off by almost 60%. Sometimes a lot less. In September, we were only off by like 6%. We had a very good estimate on September. Right, so that's the MAPE. Right, so we have these two methods so far, the MAD and the MAPE. And to this, we're going to add one more method, which is the mean squared error. So with the mean squared error, we're going to square each forecast error, and then we're going to average the squared errors. Okay, so this time we're back to something similar to MAD, right? So let's say you have this forecast method 1 gets you errors of 10 and 10. And then forecast method 2 gets you errors of 20 and 0. Which one is a better forecast? Well, according to MAD, these are equally good. Right? They both average out to 10. So what is MSE doing? MSE is saying we're going to square these. We're going to get the squared errors. Right? So let's get a different color here. Errors squared. And then we're going to average those. So we get 100 and 100. And then here we get 400 and 0. So then we average these. So then the MSE is the average of those, which is 100. And here the MSE is the average of 400 and 0, which is 200. So according to the MAD, these two scenarios are equally good, right? Being off by 10 and then being off by 10 again is equally good to being off by 20 and being off by 0. But according to MSE, this new method, the mean squared error, it's better to be off by 10 both times than it is to be off by 20 once and then right on 0 error the next time. Right? And this may reflect what's happening in your particular situation, right? Maybe if you're off by 10, that's okay. That's like within the normal amount of error your business can handle. But if your estimates are off by 20, maybe that's going to cause huge problems for your business, right? Maybe having a big error like that is going to be really bad for your business, right? Your business can handle a certain amount of error in your predictions, but when you get past a certain threshold, maybe that gets really bad for you, right? Maybe being off by 20 will get you fired, right? Well, in that case, you want to really avoid being off by big amounts like this, right? And that's what the MSE will help do, right? The MSE will prefer consistent errors that are like a moderate amount rather than this irregular big errors and small errors mixed together, even if they total the same amount. Right? So again, there's no like right answer here between what's better, MAD or MSE. It's just what's better for your situation. right? In your situation, you want to think, are these actually equally good? Are we equally happy with these two forecasts? If you're equally happy with those two forecasts, then MAD is the method that you want. On the other hand, if you think, no, I'm not equally happy, I want to avoid that big error, and I would prefer the consistent errors, then I want to go with MSE, because MSE would tell you to avoid this one and go for this one. All right, so that's the difference between MAD and MSE, right? And so which you choose is going to just depend on what you want for your particular scenario. Okay, so there's an example here, just like all the others. And in this example, right, we get the error, we subtract to get the error, but then instead of making them absolute value, we just square them all, right? And you'll notice that squaring them also gets rid of the negatives, right? So if you take a negative number and you square it, it becomes positive. So we don't, once we've squared it, we don't have to worry about the positives and negatives. So we square this, and then we average these, right? So how do we average these? We add them up and divide by 9. Right? And we get 47.63. Is that good? Is that bad? Again, by itself, it's nothing, right? You need to compare that to other forecasts, right? The whole idea here is not just, is this moving average a good forecast? It's, how does this moving average compare to other models, right? We can compare this moving average to a weighted moving average, or to an exponential smoothing, like we're going to learn later, or whatever, right? We're going to compare these to find different models, that to find which of the models that we're working with is the best. All right, so that's the MSE. Those are 3 versions. Now there's one little variant that you'll sometimes see, which is the root mean squared error, which all you're doing is you're doing the mean squared error that we just did, and you're taking the square root at the end. And the idea behind this is, like, if you look at these numbers here, right? These are in number of sales, but then when we square them, we get what? Squared sales. What are the units here? Squared sales, right? It's weird. It's a weird number of units, right? But then when we square root, if we square root this 47.63, that will get us back to number of sales again, right? And so you can fix your units that way, right? If your errors are in meters, then your MSE is going to be in square meters, which is a little bit weird sometimes, but the root MSE is going to be back to meters again, right? Or if your units were seconds, then your root MSE is going to be seconds, right? So that can be nice, just for like actually being able to say, what does it mean? How do we interpret this number? Right, but mostly we're just focusing on comparisons. So bringing it back to the data level is not super important, right? If I have 2 numbers and I'm comparing them, it doesn't really matter if I take the square root of both of them, right? Whichever one was bigger is still going to be bigger after I take the square root. All right, so those are our 3 methods. So any questions about those 3 methods? We're going to do some Excel examples of these as well in the tutorial part. Okay, so just some notes about how we actually do this in practice. In practice, what we're going to do is we're going to divide our methods up into a training set and a testing set. We're dividing our data up into a training set and a testing set before we do things, right? So when we're looking at, for instance, a weighted moving average, I told you last time that using Excel, we're going to be able to use Excel's solver tool to find the optimal weights for the data. This is called fitting optimal parameters. All right, and so we're going to use our training set to fit the optimal parameters. And then we're going to use the testing set to check the MAD or MSE or whatever. And the reason we're splitting, and then we're going to compare that to different models, right? We're going to see how does this weighted moving average model compare to, for instance, exponential smoothing model or whatever. Or a weighted moving average with a different number of periods, etc. The problem with not using a training set and a testing set, the problem with not splitting your data is because you can overfit your model. What that means when you overfit your model is that your model becomes really good at matching the training data, but not necessarily really good at matching other data, right? Like the future data, the stuff you actually want to predict, right? So if your model is overfitted to the training set, then when you look at it on the testing set, it's not going to perform very well, right? And other models are going to be better, right? So in practice, we're going to want to take our data, we're going to split it into a training set and a testing set. We're going to use the training set to fit the optimal parameters, right? To decide what weights to use for a weighted moving average, for instance. And then we're going to use the testing set to compare that to other models. All right, so we're going to see examples of this sort of training set, testing set throughout the course. This is going to apply not just to these weighted moving averages and exponential smoothing, but to a whole bunch of stuff that we're doing. All right, we're going to keep on doing this training set, testing set split. Okay, so the other thing we're doing today, our next topic, right? Before we'll do all the Excel stuff at the end, right? But before we get into the Excel stuff, we need to learn another method, which is called exponential smoothing, right? So exponential smoothing works like weighted moving averages and like moving averages in terms of it smooths the data, right? And it's going to smooth the data based on the error. So the formula goes like this, right? We have our new forecast is equal to the old forecast from last time plus alpha times the error, right? This y minus f, that's the error, right? So alpha, what is alpha? Alpha is between, it's called a parameter, it's called the smoothing parameter, and it's between 0 and 1. So when alpha is 0, what happens? Look at it for a second. The alpha is 0, then I got the new forecast is the old forecast plus 0. So in other words, the new forecast is just the old forecast. So if alpha was 0, our forecast would never change. This would be very smooth. In other words, it would be a flat line. It would be as smooth as possible. It would be 100% smoothed out, right? This probably wouldn't be very good, right? We would have no reactivity. When the data changes and our forecasts are wrong and we have these errors, then we would not react to them at all. We would just stick to the same forecast every month forever, right? Obviously, this is not great, right? We wouldn't want to set alpha all the way down to 0. That would be bad. What happens if we set alpha all the way up to 1? If we set alpha all the way up to 1, now we have the new forecast is the old forecast plus 1 times the error. In other words, f plus 1 times y minus f, that's just y, right? So the new forecast is the previous month's actual value. That's like a moving average where we only use a 1 period, right? That's a 1 period moving average. In other words, no smoothing at all, right? That's just saying my prediction for next month is whatever happened last month. right? That's just like your raw data, right? That's not smooth at all. So what alpha is doing is alpha is this way to decide how smooth do we want it. 0 is completely smooth with no reactivity, not reactive to the data at all. 1 is no smoothing, 100% reactivity, reacting 100% to every jump the data makes. Right? So what we do then is we set alpha somewhere in between. Right? If we set alpha is 0.9, that's going to be very reactive and not that smooth. If we set it at 0.1, that's going to be very smooth and not very reactive, right? And we pick out our point somewhere in between. Right? Alpha controls how smooth or how reactive this method is. Right? So this is what I was just saying here. Okay, so we're going to do some examples of it, but before we do, we just want to look at the math in a little bit more detail, because there are some useful things we can get from looking at the math. So this is called a recursive process. It's recursive because the new forecast relies on the old forecast, right? That's recursion, where your new number relies on the old number, right? Moving averages are not recursive, right? In a moving average, the new forecast relies on the previous actual values, but it has nothing to do really with the previous forecast, right? We don't use the previous forecast to calculate the new forecast when we're doing moving averages. With an exponential smoothing, we do, right? The new forecast relies on the previous forecast. So we need to know, how do we start it? Right? How do we start an exponential smoothing if we don't have a first forecast? Well, the first forecast is just going to be whatever happened in the previous time period, right? So the first data point we have, y0, is used to make our first forecast for the next period. Because then in the next period, after that, we will have a forecast and an actual value, and we'll be able to use those to make our error, to make our new forecast for period 2 and period 3 and so on recursively. This slide is showing two different ways that these are thought of, right? So we can think of it this way as being, we're taking our old forecast and we're making an adjustment based on the error, right? The y minus the f is the error, right? If the error was positive, in other words, if the actual value was higher than our forecast, then we're going to adjust things upwards. We're going to adjust our forecast upwards. And if the error was negative, if the actual value was lower than our forecast, then we're going to adjust our forecast downwards. That's one way to think of exponential smoothing. But if you just do the algebra and rearrange the formula, you can see that it's also something you can think of like this. So this is the same formula, just rearranged using algebra. So now what this looks like is, this is a weighted average of the actual value and the forecast value, right? Where the weights are alpha and 1 minus alpha. Right, so we're sort of averaging the forecast and actual values, where the actual value gets a weight of alpha, and the previous forecast gets a weight of 1 minus alpha. Right? In other words, if the alpha is 1, then all the weight's on the actual value and none of the weight is on the previous forecast. But if the alpha is 0, it's the opposite, right? Then all the weight's on the previous forecast and none of the weight's on the actual values. Right? And so usually alpha is somewhere in between. Right? So it's the same formula, but we can think of it in these two different ways. Okay, so alpha is called the smoothing constant or the smoothing parameter. We choose it, it's between 0 and 1, but also when it says we choose it, remember, we're, like I said, in Excel, we're going to be able to use solver to fit parameters. So we're going to be using Excel to find the best values for alpha. Right, and this slide is just saying what I said before, right? When alpha is higher, we're more reactive and less smooth. When alpha is lower, the model is less reactive and more smooth. And which one's better depends on what your data looks like. Right? And like I said, we're looking more in the math, right? There's a lot of just like looking deeper into the formula to get some insights on this, right? It's recursive, which means that if we take this formula here, f of t plus 1 depends on f of time t, but that depends on f of time t minus 1. And f of t minus 1 depends on f of t minus 2, and so on and so on and so on, right? In other words, all of these forecasts actually depend on all of your previous data all the way back forever. Right? If we were to try to expand it all out all the way, we would get this final line, right? And what's happening here is that your forecast depends on the previous time and the time before that and the time before that, and etc., all the way back to the first time period we have data for. In other words, your forecasts depend on all the previous data now. But it's weighted so that it depends on each prior period less and less, right? Because we have 1 minus alpha to the 1, 1 minus alpha to the 2, then 1 minus alpha to the 3, all the way down to 1 minus alpha to the t, where t is the number of periods, right? And so each time 1 minus alpha is less than 1. So taking to a bigger power, we're shrinking these weights, right? So there's almost no weight on the y0, right? The weight on the y0 is very small. The weight on the yt is quite significant, right? So we have less and less weight on prior periods going all the way back. So it's kind of like a moving average in that we're giving different weight to different periods, but it's not exactly a moving average because in a moving average, old data eventually drops out of the calculation, right? In a 4-period moving average, once something is 5 periods old, we stop caring about it, right? In a exponential smoothing, we never stop caring about it. We just care about it less and less and less as it gets older and older. Right, so exponential smoothing, nothing ever goes away. Everything stays in the formula forever. It becomes a smaller and smaller part. Okay, so it's a lot of detail, right? But in terms of the actual calculations, it's not too bad, right? So here's an example. We're going to actually do the calculations. So how does this work? We have our actual values here, right? And our first actual value was 175. So obviously we don't have a forecast here because we didn't have any prior data. We have nothing to make our forecast based on. But now that we have some data, 175, that's going to be our first forecast. Right? So our first forecast is 175. The actual value was 180. So we have some error, right? 180 minus 175 is 5. The error is 5. For this forecast, right? That's a positive error. In other words, the actual value was higher than what we forecast it would be. Okay, so what does that mean? That means that we should adjust our forecast upwards, right? So we're going to do our formula now. The new forecast is going to be the old forecast, 175, plus alpha, and that's our alpha. They've given us alpha equals 0.1, right? This is going to lead to quite a smooth forecast. Alpha times the error, which was 5, right? So the 175 plus 0.1 times 5 gets us 175.5. This is our new forecast here. Right, so we got a new forecast from the old forecast and from its error. And then we repeat. The actual value was 168, but we predicted 175.5. So what's the error now? The error is going to be 168 minus 175.5, so that's negative 7.5. Right, that's this. That's the negative 1.7, negative 7.5. And that's negative, so we're going to adjust our forecast down a bit. So we take the previous forecast, the 175.5, and we add alpha times that new error, which is going to get us something a bit lower, right? It went down from 175.5 to 174.75. And we repeat. This becomes the basis for our next one. We get alpha times the error, and we adjust again. And then we adjust again and again and again. We keep adjusting it, right? We're always adjusting our forecasts based on our errors, right? So when our forecast is higher than our actual, we adjust our forecast down. When the forecast is lower than the actual, we adjust our forecast up. And so we just keep on recursively using this formula. And that's all you have to do, right? Just use that formula over and over and over. Any questions? Okay, so like I said, we have to choose alpha. So you can choose values, or again, you can use Excel to optimize the values. But how do we optimize it? Well, we can use MAD, MAPE, or MSE, right? Picking the value of alpha that gives you the smallest possible MAD is not going to be exactly the same alpha that gives you the smallest possible MSE, right? You're going to have these different, slightly different values of alpha that are both optimal according to different criteria. Right? So using MAD or MAPE or MSE is going to give slightly different versions of which alpha is the best alpha. Right? And how different depends on your data. Right? Sometimes all three methods will more or less agree. Right? All three methods might think that the best alpha is right around the same number. It's possible, though, that they disagree a lot. Right? It's possible that the MAD thinks the best alpha is one thing, and the MAPE thinks the best alpha is a completely different thing. That is possible. Just depends on your data. All right. And right, like we said, you have to have a prior forecast to do exponential smoothing. It's recursive. We use the starting point as our starting point, the prior period's actual value, right, for our starting point. But it is possible to do the starting point in a different way, right? So you can have any method you like to get yourself a starting point. And from that starting point, you can use exponential smoothing, right? The way we got the starting point is not the only way. All right, so that's it for our exponential smoothing, right? And this version of exponential smoothing we just did, right? This is comparable to moving averages and weighted moving averages, and that it is suitable for data that does not have seasonality and that does not have trend. It's just for smoothing the random variations. All right, so we're going to take a break now, and when we come back, we will do exponential smoothing with trend, which will be a little bit more complicated. And then we'll do some Excel stuff after that. All right, it's 1:26, so we'll come back at probably about to be 1:27. We'll come back at 1:32. 1:32 will continue. Okay. We are back. So now we're going to start adding in the next thing that we need to add in, which is trend. There's going to be a couple of ways to deal with trend. One of them is to essentially deal with trend on its own using regression, and we're going to talk about that next week. And then from there, you can just, after removing the trend with regression, you can just do smoothing on the errors, essentially. And then that's fine. We can do that. But there's another method that we're going to do today, which is this exponential smoothing method we just did. We can add in another parameter, which is going to make the method keep up with trend all on its own without needing any regression. Okay, so like I said, exponential smoothing with trend today. Next week, we're going to do a linear trend line regression. Okay, so what we're going to do here in our exponential smoothing with trend, right, is we're going to have our smoothing that we just did, right? The new forecast is we take the previous forecast and then we adjust it based on the error. But then we're also going to add in a trend adjustment, right? So if there's a trend and we're just smoothing it based on error, then we're always going to be behind the trend, right? If we have our actual values are going here, 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 like this, right? And we have just exponential smoothing, then exponential smoothing, we're going to go, oh, well, this was our value last time. Well, our new value's here. Oh, we had this much error. Well, let's adjust by some portion of it. Maybe we'll do like alpha equals 0.5. So we'll go like half of the error. So our new value is here. Oh, we have this much error now. Let's adjust by half of it. Let's put our new forecast there. Oh, we still have this much error. New forecast goes here. We have this much error. New forecast goes here. Error, forecast, error, forecast, error, forecast. You can see every single one of my forecasts was too low. Well, that's bad, right? We don't want to be making forecasts that are always low. So what we're going to do then is we're actually going to do this trend adjustment. So we're going to essentially say like, all right, if we have this idea that the trend has a certain slope, right? Maybe we think the trend has a slope that looks like, I don't know, this, right? Then what we're going to do is we're going to have this trend adjustment of this much, and we're going to add that to each one of our forecasts, right? So now instead of orange, let's do brown, right? So if our previous value is this, our new value is going to be here plus that trend adjustment. So that'll put it maybe around here. And now we only have this much error. So the next time we're going to we're going to adjust by the error, make an error adjustment, but then we're also going to make the trend adjustment, right? This is what we get from the error adjustment. We started with this forecast, we went up halfway maybe, but then we're going to add the trend adjustment. We're going to add that, add that chunk on, right? And my new prediction, my new forecast is going to be like maybe here, right? Now we have only this little bit of error. So, okay, my new forecast is going to be maybe here plus the trend adjustment though, right? We have to make the trend adjustment each time. Right, we make that trend adjustment and then we get something like here. Okay, now we have this much error and we keep going. That is the idea. That is the idea behind what we're doing. Here we have the same sort of exponential smoothing thing, but we're also just adding a little bit for the trend each time. And once you have that idea in your head, the only other thing to add to that is that we are going to also be able to adjust the trend adjustment. So instead of adding the same amount each time, what we can do is that trend adjustment can slightly grow or shrink a little bit. We don't want to adjust the trend too fast, right? But what we might find is that in our data, for one part of the data, the data might have a certain slope, right? Maybe it looks like this for part of the data, but then it goes steeper for a different part of the data, or it goes shallower, right? So we want to be able to take our trend adjustment and adjust it over time. All right, so we are going to be doing the smoothing with the trend adjustment. And we're also going to be adjusting that trend adjustment. Okay, that second part is not like something we have to do, right? We could do a model where we did not adjust the trend, and we're going to see that. But it's a thing we can do. Okay, so let's get into what does that actually look like here? How does this formula work? Right, so we're putting together the forecast, the F, the smooth part, plus the trend adjustment to get the FIT, the forecast including trend. That'll be like our actual final prediction. All right, so what we're going to do is we're going to start by smoothing, right? So our new smoothed forecast is going to be the previous final forecast, right? The FIT, forecast including trend, that's like our final forecast, right? So we take our final forecast from last time, and then we add an adjustment based on alpha and what's this? This is the error again, right? This is the actual minus the final forecast. That's the error. That's how much we were off by. So when we've done this, right, we take our forecast including trend from last time, we've adjusted it based on the error, and that gets us our new smoothed forecast. But we then need to adjust for trend. Right, so now we're going to adjust this. We're going to get the new FIT by adjusting this for the trend. Oops. Right, and so then the we're going to get the new FIT for time t plus 1 is going to be the ft plus 1 plus the trend adjustment, which we're going to see in a minute. Right, just like leave aside how we get this for now. Right, this is the idea of what's happening. Right, for now, just imagine that this trend adjustment was just a number, right, based on the slope we were observing, right? Just like this number, this is the trend adjustment, not much, right? So we're always going to be adjusting every estimate by that trend adjustment, right? So we're going to take our value, we're going to smooth it a bit, right? If our previous value was too low, then our error is positive, and we're going to bump this one up. If our previous value was too high, then our error is negative, we're going to bump it down, right? But then we're going to add that trend adjustment to get the new final value, the final forecast that we want. All right, so we smooth it. This is just the exponential smoothing again, right? This is the previous forecast plus alpha times the error. All right, that's exactly what we did with the regular exponential smoothing. But now to make that a final forecast, the FIT, we have to add in our trend adjustment. Okay, so the next slide is all about that trend adjustment and how that works. Okay, so the trend adjustment also gets adjusted over time, right? So we have this new number beta, right? So for the exponential smoothing, we have alpha. For the trend adjustment, we have beta as well, right? This little typo down here. This says that alpha is between 0 and 1. Beta, it means beta. Beta should be between 0 and 1. Right? Alpha also is, right? But beta should be between 0 and 1 too. Right? So if beta equals 0, then t never changes. right? So if beta equals 0, then we're never adjusting, right? So then our trend adjustment is just going to be constant, right? So that's going to be kind of like the picture I showed you, right? Where we're smoothing based on our errors, but the trend adjustment is just a constant number, right? So you can do that. You can do a trend adjustment that does not get updated. But this also does that trend adjustment as well. So the new trend is the old trend plus beta times this. What is this ft plus 1 minus fit? Right? We might want to think about where does this number come from, right? What do I do with this ft plus 1 minus fit t? Well, if I look at this, how does this get expanded, right? What does that turn into? That is fit t plus alpha times the error. That's what goes in that circle, right? So if we do that, and then minus the fit t, what do I get? What do I get? These cancel out, don't they? I just get alpha times the error. So what is, and that's what is in this brackets, right? So they write the formula this way, but honestly, the way I always think about it is that the new trend is equal to the old trend plus beta times alpha times the error. Right? So we have alpha, which limits how fast we can adjust our smoothing. And then we have beta, which together with the alpha limits how fast we can adjust our trend. Right? And this makes sense because you generally want the trend adjustments to be smaller than the smoothing adjustments, right? We don't want our trend to be too reactive, right? Like if alpha equals 1 and beta equals 1, then the model thinks that everything is a trend. The model thinks, hey, if we went from here last time to there this time, then if there's no smoothing, what's it going to predict for next time? It's going to predict the next time is going to continue in a straight line. It's going to predict the next time's up here. Right? So there's no smoothing at all. Right? And then if it actually doesn't go up there, if it actually comes back down to where it started roughly, then it's going to think, oh, well, next time that must be the new trend. What's it going to be? Now it's going to be down here. Right? And then what's going to happen? Well, what if it actually doesn't change? Well, now it just stays the same. Right? Then it's going to think, oh, well, next time that's going to be the new trend. The new trend is that it doesn't change. Right? So then we're going to be here. Right? So if your alpha and your beta are both 1, then it's not only going to be like reactive, it's going to be super reactive. It's going to think that every time numbers go up, the next time it's going to be even higher. Right? Oh, we had a good month this month. That means the next month's going to be even better. Oh, we had a bad month this month. Oh, next month's going to be even worse. Right? That's what it's going to think all the time if you're making these 100% adjustments. Right? Which is kind of obviously too reactive. Right? It's very difficult to think of a situation where you would want your alpha and your beta to both be 1s. Right? That would be super duper reactive. You'd be over predicting everything, I think. Okay, so we've got this this trend adjustment as well. All right, and then so the next pages are just about this the math here. Right, so just like the other one, we can think of this as in 2 ways, right? There's the new trend is equal to the old trend plus the adjustment. Or we can think of it as the new trend is a weighted average between the old trend and this number, which is the difference in F's, difference in F. Right, which kind of represents like your taking away the previous trend adjustment, ignoring the previous trend adjustment, like what were the difference in smooth values? Right, which can be an indicator of what the current trend looks like. Right, this is sort of like, think of this as like current trend, the shortest term trend. Okay, so that's what's happened. That's just two ways of thinking about the same formula, right? Think of it as the recursive thing with an adjustment, or think of it as a weighted average. Right, and now I've shown you this already. I told you this was coming. I just sort of said getting ahead, right? You add them together, right? The new final prediction is the smooth value plus the trend adjustment. Okay, so this seems like it's a bit complicated, and it kind of is, right? Doing this by hand is really kind of annoying. We can do it. It's just kind of annoying because it's a lot of punching stuff in your calculator. But you can do it. Right? It's easier to do on the computer, right? We'll see on the computer it's not too bad. Right, so now we have these two smoothing constants, alpha, same as before, that's our smoothing constant, how reactive the model is to new data, and beta determines how responsive the model is to changes in trend, right? If now you have a new trend, how long does it take your model to realize that there's a new trend? Right, if trends are likely to change, then you want the beta to be relatively high, so we can get used to new trends quickly. But if the trends aren't actually changing, then having a high beta is going to make your model a little bit less accurate, because random fluctuations that are not actually reflective of new trends, that are actually just random, are going to make the model think that there's a new trend and make adjustments that it shouldn't make. Right, so depending on your data, having a higher alpha or a lower alpha might be good, and having a higher beta or a lower beta might be good. And we're going to need to use our MAD or MSE, all our various methods to evaluate what's the best alpha to use, what's the best beta to use for this particular situation. All right, so again, we need starting points. The smoothed forecast, we need a starting point there. We're going to set it to the whatever our first data point was. Right, for our first trend, right? Imagine you have one period worth of data, right? You just have a single number, right? You know that last month you made 180 sales. Okay. What's your prediction for next month? Well, it's going to be 180, isn't it? What's the trend going to be? You have no idea, right? You have no idea what the trend should be. You only have 1 month worth of sales data, right? How do you know what the trend's going to be? It might be positive. It might be negative. You don't know. You only have 1 month of data. How would you possibly know? So you're just going to set it to 0, because what else are you going to do? Right? And so then your forecast including trend is just going to be 180. Then after that, things get going for real, right? Because now you've assigned your starting values. Well, now you have an actual value coming in, right? Oh, maybe you made $210 in sales. Okay, so now you can look at this, the difference here. And what's your error? Your error is the 210 minus the 180, which is 30. And now we can start using this error and our alpha and our beta to adjust these things. Right? Let's say we have alpha equals 0.5 and beta equals 0.8. Right? So then what's our new forecast going to be? Our new forecast is going to be the old forecast, including trend, the 180, right? That is this number, plus alpha, which is 0.5, times the error, which is 30. So we're getting 195. That is our new smoothed forecast value. Now let's adjust the trend. What are we going to do for the trend? Well, the new trend should be the old trend plus alpha times beta times the error, right? So 0.5 times 0.8 times 30. Right, so 0.5 times 0.8 is 0.4 times 30 is 12. Right, so now our trend adjustment is 12. So we're going to bump that 195 up to 195 plus 12, which is going to be 207. That's our forecast for next time. And then what happens? Well, we get a new value, right? We get a new value, and then we're going to see how good was our forecast. Well, our new value is 215. Okay, so now we can get a new error. 215 minus 207 is 8. So the error was 8. So we can use this FIT and the new error to get the new prediction, right? So 207 plus 0.5 times 8. And then we can get the new trend, right? And we can continue and continue and continue, right? The new trend is going to look like 12 plus 0.5 times 0.8 times 8. And we're going to get the new trend adjustment. And then we're going to add them together to get the new FIT, and we're going to repeat forever, right? So you can see doing it by hand, pretty slow. It's pretty slow. It's not like super difficult though, right? It's just this recursive thing, right? FIT plus alpha times error gets you the new F. The new trend is the old trend plus alpha beta times the error, right? Take your new trend, add to your new F, get your new FIT. That's your final forecast. Subtract to get the new error and go on to the next step. Okay, so that's the process. That's what we're going to be doing. We're going to be getting Excel to do that for us because doing it by hand is annoyingly difficult and just slow, right? It's not really difficult, right? More just slow, right? And you can all do it, but none of you want to because it just takes forever. Okay, so here it's gonna do an example here. Right, so here we're using alpha is 0.3, beta is 0.4, and we're going to do this exponential smoothing forecast. So we have our initial values, right? The first year was 74, so we're going to set our initial values to 74 and 0. So then we get our new smooth value, 75.5. And then we get our new trend, 0.6. This is sort of similar to what I showed you, right? New trend is old trend plus 0.4 times this. Again, the slides like to do it this way. I like to do alpha times beta times the error because I find it very easy to do in Excel because I already have the error as its own column in Excel. And I already have the alpha and the beta, and it's quicker, I think. I don't know. Right? Because this 1.5 here that they're getting for this F2 minus FIT1, that 1.5 is the same as this 1.5 here on this slide. And this 1.5 was alpha times the error, right? So all they're doing on this slide is they're doing beta times alpha times the error. Right? That's all we've got here. We've got beta times alpha times the error. Right? So I like to just write it as alpha beta error. Right? And that's how I think of this one. You're free to think of it whichever way makes the most sense to you, right? If you prefer the way the slides presented, that's totally cool. It's all the same mathematically, right? Right? And then they take their new smooth value and the new trend adjustment, and they put them together to get the new FIT. Right? Which is what I was doing by hand. Right? And if you repeat that a bunch of times, you get a big table that looks like this. And so you get all these little values, and you can see what's happening here is that all of their estimates are low. Why are all their estimates low? I thought the trend adjustment was supposed to fix that. Well, this is the problem with having to start with a 0 for trend. If you start with a 0 for trend, you adjust that pretty slowly. The actual trend is probably closer to 10. Right? We're going from 70 to 120 over the course of like 6 different jumps. The trend is probably something close to 10-ish. But it takes a bunch of steps to get there. Right? Because this adjusting my trend adjustment is kind of a slow process. So when I'm starting this up, this exponential smoothing with trend, if I start trend at 0, I am going to take several periods before my trend adjustment is really locked in to a good number. And so I can expect to be behind the trend for several periods. Right? After this, after period 6, maybe I've locked in on it now. Maybe the adjustment went from like 0.6 to 1 to 2.5 to 5 to 10, and now it's going from 10.5 to 10.7. That's a small bump. Right? That's a small bump up. So the fact that we're seeing small changes in the trend adjustment means that maybe we're around the right number now. Right? We were seeing big jumps before. Right? So that was reflective of the fact that our trend adjustment was not very good at the start. It takes a few periods to get going. Right? So we can so either there's 2 ways to do this. One is just have enough data that you don't have to worry about the first few periods, right? Get your thing locked in, and then look at the later periods. If you have enough data, that's fine. But if you only have a small amount of data, then I don't know, maybe try to figure out a way to not start that at 0. Right? Try to look at what the overall trend is and maybe start it at something other than 0. That might be a better guess. Right? There's a couple of ways you might do that. Right? Looking at the linear trend from next time that we're going to do is one way you might do that. Right? We're going to talk about that next week, the linear trend thing. Right? But this is just this is what happens when you do this exponential smoothing with trend and you start with your trend at 0. It just takes a few periods to get going. Right? But after that, it works well. All right. So yeah, in the end, we end up with all these actual values, forecasts, Like I said, they're all low. Every single one is low. Why is that? It's because the trend adjustment was started at 0, right? So it was not the right trend adjustment to be making. Right? And then we can evaluate this based on MAD or MAPE or MSE. In this example, they're trying MSE. Right? So what is our MSE? Our MSE is 2774.06. Again, is that good or bad? It's neither, right? It's only good or bad compared to other models. We could compare this to some other model that we were doing. And then see what we get. See which one's better. Oh, sorry, that's not the MSE, right? The MSE is the average. That's the total. The average is you divide the total by 6 because there's 6 of them, right? So the MSE is actually 462, right? But everything else I said was correct, right? Is that good? Is that bad? We don't know. It depends on how well other models are doing, right? It's competitive, right? You want to compare this model to other models to see which one to use. All right, so that's the exponential smoothing with trend, and we can have a short break now because this is the end of the lecture part. And we're going to go on to Excel. So we'll start back up at 210, but in that time, I want you to open the Excel file, right? On ideas in module 2, right? There's an Excel file called week 2 tutorial data. I need you to open that up during this break. All right, so that you're ready at 210 for us to start the next part. All right, and of course, if anyone has questions, feel free to ask. I know that, people ask fewer questions online. That's one of the reasons I like in person. People are more willing to pipe up when they have a question. All right, see you in 5. Okay, so let's get started on the Excel stuff. So we have this data, right? There's these different parts of the Excel sheet. There's also some tutorial slides, which give us the questions that we're going to use. Which I'll just, if you have that open, you can look yourself. But if you don't, I'll just share my screen with you on that. Right? We have this data, and we have these 4 questions, right? Looking at the data, what do you think is going to be accurate? Exponential smoothing or exponential smoothing with trend? And then we're going to try both. We're going to try an exponential smoothing with alpha 0.7. And then we're going to try exponential smoothing with trend using alpha 0.4, beta 0.8. And then we're going to compare the two. Okay, and then after that, that's going to be, the simple part. But then after that, I'm going to show you some stuff with Solver so we can actually optimize these alphas and betas and see what we can do with that. Okay, but this is where we're going to start. Right, so the first thing we might want when we're looking at data like this is to well, let me move this annoying bar away. We want to go insert a line chart and then just do the first line chart, right? We can see what the data looks like. So just looking at this data, looks like there's an upwards trend, right? We can fix our axis labels like you would have seen us do in what was that stat? The RAPP 5004 or whatever, we would have done that, fixing the axis labels. Be 0 to 10 instead of 1 to 11. Anyway, right? But there seems to be a trend, right? This is the overall point I want to get at, is that there seems to be a trend. The numbers seem to be getting higher over time. Looking at this, I would guess that exponential smoothing with trend is probably going to do better than just a regular exponential smoothing. Okay, so now for part B, we're going to actually do this exponential smoothing. Right? So what's our exponential smoothing? Honestly, I want to insert a row in between here, which is just the error. Right? Just because that error is going to be useful. Right? So we have the first exponential smoothing forecast is 4,000. Right? Why is it 4,000? Because it's equal to this one. Right? We don't have an exponential smoothing up here. There's nothing up here. Right? But here we have 4,000. That's our starting point. What's the error? Well, the error should be just the actual minus the forecast. Whoops, that's the wrong format. That is formatted as percentage. I want that just to be number. And that's fine. Actually, I'll keep 2 decimal places. For absolute percent error, we want to do that is the error divided by the actual. And you can see this is already in the percentage format, so that's good. Right? If that wasn't in percentage, it would look like this. Right? In percentage, like that. Right? You don't have to type in the times 100, in other words. Right? Don't type the times 100 into the formula here. You don't need to, right? Because Excel handles that automatically when you just change the format to percentage. Okay, so we're almost ready to go now, but we just need to do the actual exponential smoothing formula. So how do we do this? Well, we need an alpha. Okay, so what's alpha? Alpha, they told us to use 0.7. Okay, so I'm going to do the previous forecast plus alpha, which I'm going to make static because I don't want that one to move, times the previous error. Right? This is why I wanted that error column. You can do this all without that error column, but it makes your formulas more complicated. I'd rather have more columns and simpler formulas. I think that makes the sheet easier to understand for anyone else who has to come in and edit it later, right? As you know, when you're working with other people, which you almost always are, it's important that what you've done is transparent, right? So having simpler formulas and more columns with more explanation is better. It's the same with programming, right? When you're programming, you'd rather have simple methods, but more methods rather than have like one big method that tries to do everything at once and that no one but you understands. Okay, so we've got our forecast. So now all we need to do is we need to copy and paste these all the way down. And then we'll copy and paste this. Oops, I should have pasted formulas just to not mess up the formatting. Oops, and I didn't do absolute value. I noticed there's a mistake, right? Because that shouldn't be negative. I'm going to copy and paste this down and I'm going to fix that mistake. Copy and paste formulas. Okay, so I don't want negatives. Negatives are bad here for the absolute percent error. So I'm going to do equals, not just this, but ABS brackets, this over that, right? ABS is just absolute value. Right, so now I'm going to copy and paste that down, paste formulas. Now I have my absolute percent error. All the negatives are gone. Right, I want the negatives here because I need no negative or positive when I'm making my adjustments here. Making those all have the same number of decimal places just for making it uniform. All right, but there we go. Now I have my different forecasts and my actual values. I have all my errors. I have my absolute percent errors. And then for the MAPE, what's that going to be? Well, that's just going to be the average of the absolute percent errors. 23.56%. All right, and you can see that's going to depend on alpha. If I change the alpha to 0.4, it changes. Right, it can get better or it can get worse depending on what I do. Right, 0.1 is really bad. Alpha equals 0.1, not working for me at all. 0.9, better. 0.7, even better. Right? Okay. Now we're going to do exponential smoothing with trend. So again, I'm going to want to just stick in a little error column because that's going to be helpful. Okay, so how do we start? Remember, we have nothing to start with. Right, nothing to start with. Right, what are our starting values? Well, here, our initial forecast is just the previous data, right? The trend starts at 0. And then my forecast, including trend, is going to be this plus that. Right, and that's going to be the formula for FIT the whole way down. right? So once I have this in, I can copy and paste that down the whole way. Right, and then my error, what's my error? My error is going to be the actual value minus the FIT. And again, once that's in, I can copy and paste that down the whole way, because that's always the formula. Right, my absolute percent error is going to be equals ABS of this over the actual. And once that's in, I can copy and paste that down the whole way. Right, so these three formulas are all set. Right, I'll give you a sec to catch up. Right, so the 4,000 and the 0 were our starting values. The FIT is always going to be smoothed plus trend. The error is always going to be actual minus FIT. And the APE is going to be my error over actual, and then absolute value of that. And then once you're caught up with that, we can go on to making our new smoothed forecasts and our new trend adjustments. If I'm going too fast, please tell me. It's much easier to tell in person, right? Because in person, I can see who's still typing and stuff like that. So it's very possible I go too fast online and don't know it. And I won't know unless you tell me. All right, sorry, go ahead.
What's the errors formula again?
The error is just going to be the actual minus the forecast including trend. Right?
Trend.
Minus FIT. So then before we move on, we're going to need alpha and beta. And the question gave us 0.4 and 0.3, I believe, in the PowerPoint. No, 0.4 and 0.8. Those are my alpha and my beta that it gave me.
Is the formula for absolute percentage error?
The formula for absolute percentage error is equals ABS of the error divided by the actual. All right, it's E over Y, essentially. All right, if I'm going to annotate this, right, I've got, this is my Y, this is my F, this is my T, this is my FIT, this is my E. Okay, so all of these formulas can be just copied and pasted down because they're all correct. And then and then the numbers are gonna be correct once we fix these, right? We gotta get these in place and then everything's gonna work together like a nice machine and get everything working for us. So my new smoothed forecast, right? How does this work? This is equal to the old FIT, not the old F, right? It's the old FIT plus alpha, which needs to be static. So let's put dollar signs on that, times the previous error. That's my smooth forecast. And then my new trend adjustment is going to be the old trend adjustment plus alpha times beta times the previous error. And oops, the alpha and the beta should both be static. Right? You can do this with a different formula, right? You can do the same thing with the version where it's like f minus fit or whatever. You can do that. It's fine, but this is the way I prefer to do it. You would get the same thing if you use the version that's on the slides, though. Right? They're mathematically identical. And then once you have these, you can copy and paste them down. I'm going to paste formulas, and I'm going to get my trend adjustments, and I get all these, and there we go. Right, so then I can find out what my MAPE is. And that's going to be the average of these. $21.26. Okay, so we have all of our formulas in. We have our MAPE. We notice that things are better for the last chunk than they were for the first chunk. I mean, the first chunk had this one, which was a really accurate prediction, but like it had some real bad predictions too, right? But then it got a bit better. That's, I think, to do with the fact that the trend adjustment starting at 0 was not up to speed. I think the actual trend is probably quite a bit larger than 0, right? And it takes some time to figure that out. Yeah, so that's 21.26. Again, this depends on the alpha and the beta. If we change our alpha to 0.7, oh, it gets worse, right? That made it worse. If we change it to 0.1, 22.69 compared to 0.4, right? The 0.4 is actually quite a bit better, right? So it's interesting, right? Changing this 0.4 to a 0.7 makes it worse. But on the other one, changing that 0.7 to a 0.4 makes it worse, right? So the best alpha for exponential smoothing without trend is not necessarily the best alpha for exponential smoothing with trend, right? We're going to use solver to figure out what is the best, right? But if we're just comparing these two, then we can say that the one with trend looks better, right? And that would be, for our summary, we can put the two forecasts in here, right? So I can say this one is from section B, and this one is from section C, the FIT, and then I can just copy and paste those formulas down, and we can get the two different forecasts. Right, these are my two different forecasts. In my summary, right? But based on the MAPE, I like the version with trend better. I think the version with trend is doing a better job based on MAPE. Right? If we did MAD, MAD may or may not agree, right? If we did MSE, MSE may or may not agree. We don't know. We wouldn't know unless we tried it, right? It's often the case that MAD and MAPE and MSE all agree on which of two models is the better model, but it's not a guarantee, right? Sometimes they disagree. Any questions so far? So the next thing I want to show you is once you've got all this in using formulas properly and everything, I want to show you how to use solver to get the smallest possible MAPE for this method. Right? So if I go to let me move this bar out of the way. If I go to data, I have solver here. You may not have that by default, right? So if you want to get solver and you don't have it, you're going to go file, options, add-ins, and then click on go, and then check off the solver add-in. Right, so that's file, options, add-ins, and then click on go. Not okay, click on go, then check off the solver add-in and click OK. And when you do that, once you've done that, you should have solver up here in the data section. It may be slightly different on a Mac. I don't know. I don't have a Mac. All right, so if you've got using some Apple product, then it may be a little different. You can look up how to get it, but it should still be available. All right. Either way, we have solver, right? So once we have solver, if I click on solver, I'm going to be able to use solver to minimize my MAPE. So it says set objective. So I'm going to select the objective cell is the MAPE, right? That 23.56%. That's my objective cell. And it says to max min value. I want to minimize that. By changing variable cells, I want to change this variable cell, the alpha. Now, are there any constraints? Yes, there are, right? The alpha has to be between 0 and 1, right? So this checkbox, that makes sure that alpha is greater than or equal to 0 if we have it on, right? So leaving this on, make sure alpha is greater than or equal to 0. But if we want to make sure alpha is less than or equal to 1, then we need to add a constraint. Right, that constraint will say that alpha, this cell reference, should be less than or equal to 1. And then the solving method should be non-linear. We are not doing simplex LP or evolutionary. This is not linear. So doing simplex LP will not work. Right, this is a non-linear thing. It's called exponential smoothing. It's this big recursive thing. It's definitely not linear. So GRG nonlinear is the method we need. So this is what it should look like. Once you have it all like this, if yours looks identical to this, then clicking solve is going to do it for you, right? So the objective, remember, was the MAPE, which we are trying to minimize. And we're doing that by changing the alpha. Subject to the constraints that alpha has to be less than or equal to 1. We want this checkbox on to make sure alpha is not negative, right? It needs to be between 0 and 1. So this combination will do that for us. We're using the GRG nonlinear method, and we're clicking solve, and there we go. The optimal alpha is 0.616. This is the best we can do. All right, and then we can go over to this one and we can do the same thing. All right, so the best we can do is an MAPE of 22.87%. Over here, we're already beating that, but let's see how badly we can beat. Let's see how much better we can do. And we do better by changing these. All right, so again, we're going to go to solver, set objective. Objective is going to be the MAPE. We're going to minimize it, and we're going to do that by changing the variable cells alpha and beta. 0.4 and the 0.8. Subject to the constraints, we're going to add a constraint. Both of these have to be less than or equal to 1. You can do them together. That's allowed. You can do them together, highlight them both, less than or equal to 1. That means that each one of those is less than or equal to 1. This is really two constraints in one. This checkbox makes sure that both of them are greater than or equal to 0. And then nonlinear. All right, so that's how it should look. Very similar to last time. All right, the objective is the MAPE. We're minimizing it. The variable cells we're changing are the alpha and the beta. And they should both be less than or equal to 1. And they should both be non-negative. And with that, we click solve. And we get this. Oops, I clicked on the X. Redo that. I forgot to click accept. Solve. Keep the solver solution. We can get all the way down under 18%. We can get all the way down to 17.79%. And the way we do that is by having a relatively low alpha. So we're not smoothing very much. But our beta is all the way at 1. That means we want to be updating that trend quick, right? We want our trends to update fast. That is what's going to be doing the best for this particular data, right? That's not always going to work for every data, right? Different data is going to have different requirements, but for this one, this is going to be the best. All right, any questions? Okay, so that's the sort of thing you have to be able to do for your assignments, for your tests and stuff. You have to be able to, when given alpha or beta, implement these models, right? The exponential smoothing model and the exponential smoothing with trend model. You have to be able, with one of these models, to calculate the MAD or the MSE or the MAPE, right? And you have to be able to use solver to minimize that that measurement, whether it's the MAD, MSE, MAPE. You have to minimize that by adjusting the parameters of the model using solver. Okay, so those are all the things you want to be able to do. All right, so implement exponential smoothing and exponential smoothing with trend. You want to implement MAD, MSE, and MAPE. You want to be able to use solver to optimize parameters. And on that note, before we go for the day, I want to show you using solver to optimize weighted moving average weights. Okay, so we're going to do that over on page A. I'm going to do a 4-period weighted moving average. And so what are my weights? I'm going to need some weights. All right, so what are my weights going to be? Well, I'm just going to start off at 0.25 each. Right, I'm going to start off with weights of 1/4, equal weights. You could also think of that as being 1, 1, 1, 1. That's actually the same, right? As long as all your weights are equal. So this is going to be the same as just a regular moving average. So what am I going to do then? I'm going to implement my weighted moving average formula. Remember what that was? Sum product of these, which are static, and these, which are not static, divided by the sum of these, which are static. Sure, that's all static, right? And then I can bring that down, and these are my weighted moving averages. And then I can calculate the errors, right? This is just actual minus forecast. Down. And then I can do my absolute percentage error, right, which is going to be my error divided by my actual, but absolute of that, ABS of that. Make that percentage format. Copy that down. Right, so I'm going a little bit quick because we've done all this before, right? We did the weighted moving average formula before with sum product. We did the error, we did the APE. You can find the MAPE is equal to the average of those. All right, so right now, this is not great. Here, let me make these bigger. Make that bigger, make it easier for you to read.
Can we go back on the 450 formula again? The first time, the first.
Yep. Yep, this
Yeah.
one, right, that's my weighted moving average formula. That's my sum product formula.
D2, D5.
All right, my weights, sum product of weights with data divided by the sum of the weights.
Okay.
Yeah. So there's one thing we want to think about with these weights, right? Which is when we're doing this method, if I come back and I say, oh, the correct weights are 1, 1, 1, and 1, and you say, no, the correct weights are 3, 3, 3, and 3, who's right? Well, right, we're both right, right? These are actually the same answer. Right? If I say all the weights are equal and you say all the weights are equal, then we're actually making the same predictions. Right? You can see the MAP is 27.07. If you change these all to ones, then it's still 27.07 because it's the same. We're making the same forecasts. These are the same. So one thing we might want to do is we might want to standardize our weights. Right? In other words, we want to force the weights to add up to 1. Right? So right now my weights add up to 4, but I can force them to add up to 1. And the reason we would do that maybe is because then if you got the same answer as me, it would be obvious that you got the same answer as me because they would literally the same weights, as opposed to, you know, us actually making the same predictions, but having weights that look different just because yours add up to 5 and mine add up to 10 or whatever, right? They could be exactly equivalent, but look different. Right? If we force them to add up to the same number, right? If we force our weights to add up to 1, then we're going to have the same answer and it's going to look the same. All right, so this is not strictly required. We can optimize our weights without doing this, but this is just a helpful thing, right? To standardize our weights. So how are we going to optimize these? Well, same as before, right? We're going to go to solver. We're going to set the objective. The objective is the MAPE. We're going to minimize that, and we're going to do that by changing the weights, D2 to D5 on this chart. What are the constraints? Well, we don't want our weights to be negative. Generally speaking, negative weights are weird. We probably don't want those. There may be some problems where having negative weights is actually helpful. So like, you could try uncheck the box and see what happens. Maybe it's actually useful to have negative weights. We'll try that later. We're going to try it first with positive weights. We're going to see what we get. The constraint I'm going to add is that the sum of the weights must be equal to 1. Right? I'm adding in that constraint. That's the sum of the weights is equal to 1. That's my standardizing the weights part. Right? It's not required to do that, but if you don't do that, then you and some other person are going to get answers that are actually equivalent but look different. All right, so now I'm going to click solve, and it's going to give me, hopefully, an answer. Okay. Cool, so it's got a solution. It thinks the best thing to do is to give 2/3 of the weight to the most recent period, no weight to the second most recent period, and then about 1/3 of the weight the period before that, and then no weight to the period before that. That's kind of neat and interesting and a little bit weird, but all right. And it gives a pretty good MAPE, right? 18.5. Right? That's better than my exponential smoothing. That's better than my best exponential smoothing. It's not quite as good as my best exponential smoothing with trend, but it's close. Right? This is pretty good. Right? So these are the best weights it can do. Right? This is how we would optimize our weights. And like I said, what happens if you uncheck this? If you allow the weights to be negative? Well, in this case, nothing. It actually sticks with its answer. Right? But there would be other times where it might go like, okay, let's throw in a negative weight here. Why not? And that might actually improve the predictions. Right? In this case, like putting a negative weight in probably makes things worse in this particular example, but there would be times when a negative weight could potentially help. Actually, hold on. Okay, yeah, so sometimes you want to vary your starting point because there's some noise here. In this case, by varying my starting point, I actually got a better answer. And so this is a limitation of the solver tool. When you have a bunch of parameters and you have a non-linear thing, it's not always going to find the best. It's going to find what you might call like a local minimum, right? So it's going to find something where it can't find anything else better in the vicinity, but it's not always going to be able to find the absolute minimum. And so sometimes if you just like change these to random stuff, 5, 10, 9, and 12. And now let's run this again. You get a different answer. Right? In this case, it likes these negative weights. Right? And same with negative weights, I can get even better MAP. I can even do better than the exponential smoothing with trend by using these positive and negative weights. Right? Which is very interesting. This weight is more than 100%, but it's counteracted by negative weights. Kind of weird, right? But you know, this is a model you could use, and it could be suitable for some things, but also we could just be overfitting, right? What it's done is it's managed to get 3 predictions that are almost right on. This one, and this one have basically 0 error, which really helps with the MAPE. So if this was our training set and we had another testing set, I'm really not confident that this would actually do that great. This could just be overfitting the data. Right? Could very easily be overfitting the data. right? So this method with solver, it has some real downsides, right? First of all, the solver is not the best tool, right? There are mathematical tools that will actually do better at optimizing than Excel's solver tool, right? Excel isn't the most powerful math package that there is, right? So, you know, sometimes we can just do better than Excel. And then this comes into play because when we look at Excel, right, we don't always get consistent answers. Right? By changing our starting positions, we can get slightly different answers. I had that problem on an assignment once. Everyone came back with different answers on the assignment. I'm like, oh, they all did it wrong. And then I realized, oh no, they didn't all do it wrong. They just all started with different starting points. So I try to watch out for that on the assignments. Could happen on your assignment. All right, so solver has some limitations. Especially when you remove certain restrictions, right? Like allowing the weights to be negative allows solver a lot more freedom. And so you can get very different results depending on where you start sometimes. And the more freedom you have, right? The more freedom you give a program like this, the better the chances are that you're overfitting, right? We're going to see that with regression. It's really easy to overfit your data if you have a lot of predictors. If you have a lot of different X values, a lot of independent variables, it's very easy to overfit your data. So it's the same idea here, right? With this weighted moving average, having 4 parameters, it's easier to overfit the data than it was with only 2 parameters or only 1 parameter. Right, so this is which is exactly why we want to have the training set and the testing set, because the testing set is going to weed out those overfitted models. Those overfitted models are going to perform worse on the test set. Okay. So that's it for today. That's all we've got. Anyone have any questions?
Hi, I just want to know when the recording will be posted.
Good question. It's going to take a little bit of time for Zoom to encode the recording, but I should post this sometime this evening.
Thank you.
Yeah, it'll like send me an email in an hour or something, but I'll probably be busy picking up my kids from school then, so I'll get it posted later. Okay. So see you next week, probably back in person again. And if you have any questions about the quizzes or anything, in the meantime, let me know. Remember your quiz number 1 is due on Sunday.
Thank you.
Yep, you're welcome. Have a good day, everyone. Bye.
Thanks. Bye-bye.